A quantum system in superposition exists as a blur of simultaneous possibilities. The paradox at the heart of quantum mechanics is asking why observing this chaotic overlap forces it to yield a single, definite outcome. To explain how this blur resolves into a single reality when measured, traditional physics relies on the Copenhagen interpretation. It introduces a physical collapse postulate, an ad hoc mechanism that forces the wave function to snap into a definite state the moment it is observed. Other models attempt to resolve this by adding untested physical laws. Objective collapse models, for instance, inject entirely new dynamical parameters into the universe to force that single outcome to happen spontaneously, independent of an observer. The Information Manifold Model, or IMM, takes a different path. It seeks to resolve the measurement problem without adding any new physical mechanisms or phantom forces to reality. But before the IMM can propose a mathematical solution, it has to address a fatal flaw in modern theoretical physics, our sloppy use of language. When physicists use words like projection, observation, or state, they bring immense, often unacknowledged conceptual baggage into the equations, corrupting the structural arguments before they even begin. To solve physical paradoxes, we have to recognize that our linguistic ambiguity often creates the very paradoxes we are trying to solve. The IMM's foundational document, Paper 0A, identifies this as the substitution error. This happens when a reader silently replaces a strict technical term with its everyday meaning. When this semantic drift occurs, a theoretical framework is suddenly forced to defend ghost arguments it never actually made. To stop this, the IMM locks down its vocabulary, paying special attention to epistemic operators. An epistemic operator is the exact label a framework uses to state what it claims to have done, whether it derived a result, hypothesized a conjecture, or assumed a premise. Paper 0A enforces a strict lexical contract. Every single epistemic operator must carry explicit operational consequences before a single equation is presented. Under this contract, claiming derivation requires a strict, unbroken logical chain traced directly from axioms. In contrast, an ansätze openly acknowledges that an assumption is made to make a calculation tractable. Without this strict lexical discipline, advanced physical frameworks inevitably overstate their results and collapse under internal inconsistencies. IMM Paper 2 serves as the ultimate test case for this discipline. It sets out to prove quantum determinacy using only rigorously defined, locked-in terms. By accepting this rigid contract, we strip away intuitive biases. What remains is the raw, verifiable mathematical structure, ready to be evaluated on its own terms. We begin building this architecture by locking in the definition of a foundational state. Within the IIM, a state is not a physical configuration of particles in three-dimensional space, nor is it a subjective mental state of an observer. A state is defined purely as an admissible point within a larger structural framework. It is a coordinate of information. All of these admissible informational configurations exist within the information manifold, denoted as M. This is the full, abstract state space, containing every possible configuration. This manifold represents pure relational geometry, explicitly distinct from physical spacetime. Below this vast structure lies the experiential space, denoted as O or E. This is a separate, lower-dimensional space, containing only the reduced outputs accessible to an observer. By strictly separating the underlying informational reality of the manifold from the observer's limited access point, we create a purely structural arena. Here, the act of measurement can be modeled as a strict mathematical mapping between two spaces. This mapping brings us to axiom A3, the foundational structural commitment of the IMM. It models observation as a specific type of connection between the high-dimensional manifold and the lower-dimensional observer space. This diagram illustrates that connection.
Observation is modeled as a projection, denoted by pi, mapping the high-dimensional manifold down to the observer space. Its defining feature is being many to one. Multiple, distinct informational states on the manifold map down to the exact same outcome. This structure leads directly to Theorem 4.1, structural determinacy, proving every observation produces exactly one outcome. The proof is immediate. Axiom A3 defines observation as a mathematical function. By definition, a function maps any given input to exactly one output. Applying our epistemic check, this proof requires 0 physical collapse postulates and 0 assumed physical mechanisms. The superposition problem is structurally dissolved. Quantum collapse is not a violent physical event. It is simply the mathematical consequence of a many-to-one projection. We must immediately invoke the lexical contract to prevent overinterpreting this result. We have to draw a strict boundary between a cardinality determinacy, proving that exactly one outcome occurs, and identity determinacy, which would prove which specific outcome occurs. Theorem 4.1 establishes cardinality determinacy. It proves there is one outcome, but not which one. Because the projection is many-to-one, multiple input states collapse into a single point. Information is fundamentally lost during this process. Look at the text annotation on the bottom left of this chart. An observer in the lower dimensional space holding a specific outcome cannot mathematically reverse the function to see the original state on the manifold. Discovering which outcome occurs requires deriving probability measures, specifically the Born rule. That is a separate problem requiring different mathematical machinery, addressed later in IMM Paper 4. Recognizing this limitation is not a weakness. It demonstrates structural realism and epistemic honesty. Accurately defining the boundaries of a mathematical proof protects the framework from the exact type of overclaiming that routinely destroys other theoretical models. We can now evaluate the structural cost of the IMM solution against legacy quantum interpretations. This comparison matrix maps it out. The Copenhagen interpretation requires an arbitrary axiom 5 to force wave function collapse. Everett's many worlds interpretation avoids collapse but incurs massive structural debt by requiring the universe to constantly split. Objective collapse models like GRW attempt a mechanical fix. They inject entirely new dynamical parameters into reality just to force that single outcome to occur. Bohmian mechanics is structurally similar to the IMM in that it posits a full configuration space, but it requires the addition of a physical, non-local pilot wave to guide the outcome. The Information Manifold Model achieves the exact same single outcome determinacy using 0 new physical laws, 0 extra dimensions, and 0 arbitrary variables. It relies entirely on the mathematical property of the projection. Applying Occam's razor to these structures, the IMM demonstrates that mathematical geometry is a vastly cheaper, more elegant solution than inventing ad hoc physical forces. For the IMM to stand as a valid physical framework, it cannot just be mathematically consistent, it must be empirically falsifiable. Look at failure condition item 1. If observation acts as a relation, implying hidden collapse, the framework shatters. At item 4, if experiments fail to show predicted Born rule deviations, axiom A3 is disproven and the theory is falsified. These strict vulnerabilities are exactly what make the framework powerful. It stakes its survival on testable geometry, not on philosophical wordplay. This elegant dissolution of the quantum measurement problem was only possible because of the lexical contract established in Paper 0A. By refusing to let inherited words like collapse dictate the math, the framework uncovered the underlying function mapping reality to experience. The deepest mysteries of quantum mechanics might not require discovering new physical particles or mapping multiverse branches. They may simply require the discipline to build models out of rigorous, unyielding mathematical logic.